Okay, today we are going to study the lecture number 17 for Mechanics of Solids course, and the lecture is about unsymmetrical bending. The instructions are also given you in the previous class as well. It remains the same. We will be doing the interactive sessions for this course as well, just like the structure analysis course. And I would suggest you to keep your calculators and notes with you in all the lectures and keep making notes, because for this course, strictly the numericals I will be solving on the whiteboard. And if you have any question, you can turn off your mic and you can ask me. And another thing that I want to suggest is you should try to use your mouse with your laptop or your computers, and you can ask me or I will ask you to request for the access to whiteboard while I am solving the questions. So you can also solve the questions on the whiteboard if it's required. And for the assessments, I will be posting the assignments regularly on CMS or on your Zimbra, so you should keep a check on it. And quizzes will be conducted on MS Forms or whichever format suits better. And if you have any question, you can ask me via email or in the class groups on MS Teams or WhatsApp, whichever suits you well. So moving on, firstly, I would like to review some of the topics that we have covered in this course. Basically, we broadly, if I say, we covered one topic in this course, that is calculation of stresses and strains. So the first thing that we studied was how to calculate the shear stresses in different kind of members, such as beams. I think we studied beams, yeah. And then we calculated the stresses when combined loadings were acting on a structure. For example, for a beam, if a perpendicular load was acting and a horizontal load was acting on a beam, then we calculated the stresses due to the combined effect of these loads. And the combined stresses include the shear stress, the flexural stress, and the axial stress. Then we studied how to transform the stresses onto different axes or planes by using the equation of transformation and Mohr circle. The same thing we studied for the strains, how to transform the strains onto different planes or axes by using the Mohr strain circle and the transformation equation. And finally, we studied the strain rosettes to calculate the strain in a member experimentally. And basically, this defines the whole topic. From experimentally, we use strain rosettes to calculate the strain. Then we transform it into onto different axes, and after that, we can calculate the stresses using the strains, and we can transform these stresses. And then, if we have the stresses, we can calculate the stress due to the combined impact of the loading. So these are the topics that we covered pre-midterms. After midterms, we are going to study the major topic is unsymmetrical bending, and the first topic is this one. The second is we will be studying the stresses in different cylinders, which include thick and thin cylinders. Third one, we will be studying the calculation of forces in the curved beams. Up till now, we have been studying the stresses or the forces in the straight or prismatic sections, but now we'll be moving towards the curved beams as well. The fourth topic is the eccentrically loaded columns, for which we will be studying the secant formula to resolve this eccentrically loaded column or to calculate the forces in these kind of columns. And finally, we will be studying the topic of we will be studying the theories of failures. There are different kind of theories like von Mises or something like this. That is the last topic for this course, and we obviously will be solving a lot of example problems for all these courses. The textbooks, obviously, we have been using the Strength of Material by Pytel and Singer, but for the topics after midterm, I would suggest you to consider these two textbooks. The book of Mechanics of Materials by Pytel, the second edition I am following, but you can use any edition which you have. And then the second reference should be to the Mechanics of Material by R.C. Hipler. But basically, all three of them are the textbooks, and you can use anyone, but I would recommend you to use to give this book as first preference, and you will get the access to this one. Moving on to the topic, today we are going to study basically the unsymmetrical bending. But before moving on to the actual topic, we need to review some of the basic concepts of mechanics and to understand different type of sections. If we understand all these definitions clearly, they are confusing things and you will get confused, I know for sure. But try to see physically what every single concept and every single definition means. I'll try to explain it better, and if you have any question, you can ask me during the lectures. So the first thing is, what is axis of symmetry? Let's move on to the whiteboard. If, for example, I have a rectangular section, and this is the centroidal axis passing through the centroid of the rectangle. Now, around this, let's say this is the y-axis, and around this y-axis, I have this shape, which I will show in the red one, this shape. Okay. Now this shape is basically the mirror image of the shape of the rectangle on the left side. So what is axis of symmetry? Axis of symmetry is the one around which a body or a section have a mirror image of the other side. Is there any question? So for example, let's look at this one. This is a rectangular body, and what is axis of symmetry? That divides the section in such a way that one part is the mirror image of the other part. Let's look at this section. This is the axis, and around this, it divides the section into two parts, and each part is the mirror image of the other part. So this is my axis of symmetry. What about this axis? Let's call it an x-axis. Around this axis, also one part is the mirror image of the other part. So this is also an axis of symmetry. So for this section, can I say that it has two axes of symmetry? Okay. Now let's look at the example of this I section. In this I section, one is this, let's say y-axis, the other one is this x-axis. Now both these axes divide the section in such a way that each part is the mirror image of the other one. So for this I section also, we have two axes of symmetry, this x-axis and the y-axis. And for this t-axis, now this is important. Let's look at this x-axis. Now this x-axis, although is dividing the t section into two parts, but this bottom part is not the mirror image of this upper part. So we cannot say that this x-axis is the axis of symmetry, but this y-axis is the axis of symmetry because it divides the t section into two parts, and this left part is the mirror image of the right part. Okay, so this is how you define axis of symmetry. Now let's look at this L section. Now in this L section, these are the two centroidal axes. You know how to find the centroid of the body. Now these are the two centroidal axes, and around both these axes are dividing the L section into two parts. But both of these axes are not symmetrical axes because both these parts are not the mirror image of the other one. So there is no symmetrical axis in this L section, and same is the case with this Z axis. There is no mirror image of the two parts. So what is a symmetrical section? Symmetrical section is a one which has at least one axis of symmetry. So we can say that this is the symmetrical section, this is also the symmetrical section, and this T shape or the T section is also the symmetrical section because it has one symmetrical axis. And both these sections are unsymmetrical section because they don't have any symmetrical axis. And not just the straight axis, you can also try looking by dividing the beam in dividing the section into inclined shapes by passing an inclined axis through them. And you can see whichever axis you pass through them, there won't be any orientation around which one part forms the mirror image of the other part. So these are basically the symmetrical sections and unsymmetrical sections. Moving on, I will explain now what is the neutral surfaces and neutral axis. Let's say this is a beam. which is supported or simply supported beam. And if I apply the load from this direction, the beam will deflect or bend in a shape something like this. Now we know that there will be an axis or a surface in the beam which does not go on any type of which does not have any type of compressive stress or the tensile stress. No compressive and tensile stress. So for the case of symmetrical section or the rectangular section, this surface is located at the center of the section. For example, this surface or this one. Now this surface which does not undergo any type of bending, be it the tensile or be it the compressive, is known as neutral surface, right? And the axis which is perpendicular to this neutral surface is known as neutral axis. Now, what is basically the neutral axis? Now, the beam will deflect something like this. And let's say the moments that are produced at the two ends are something like this one. And if I look at into the section, the moment will be acting around this axis. I will call it the z-axis. From this figure, you will understand it better. Now let's assume that this is the rectangular beam that we have plotted over on the whiteboard. And if the load is acting in this direction, the beam will deflect something like this. And the moment is being produced around this axis, this x-axis in this figure. Now this axis is perpendicular to the neutral surfaces, which is this one. Now the neutral surface is one which does not undergo any sort of extension or tensile or compression stresses. And the axis which is perpendicular to this neutral surface or the axis around which bending is taking place is known as neutral axis. Now in this case, the neutral axis is the x-axis. But I have a question for you. Do you think that there will be how many neutral axes can be in a beam? Anyone?
सर ये तो उसकी शेप पे डिपेंड करता है. अगर सर्कल हो तो, अगर ये सिलेंडर हो फिर तो अनलिमिटेड न्यूट्रल एक्सिस हो जाएंगे. ये उसकी शेप पे डिपेंड करता है सर.
It depends on the shape, so you say that. Yes. Anyone else? Harun.
Sir, only one हो सकता है.
Okay, only one. Harun, where are you? Where is Harun?
Sir, either you. Sir, I guess 3, 15.
सर वो लोड भी होगा ना. सर वो लोड पे भी डिपेंड करता है, लोड किस डायरेक्शन में लग रहा है. खाली मतलब बगैर लोड के तो न्यूट्रल सरफेस होगी नहीं.
Okay, yeah, you're right. Actually, which one is a neutral axis is not a fixed axis in any type of a beam. It completely depends on the direction of loading, that which is our what is our neutral axis. For example, let me show you this beam. In this beam, it is, let's suppose this is a similar beam. If the load is acting in this direction, then the bending is taking place around this axis that I've shown with the red marker, around this axis. So now in this case, this is my neutral axis. Okay. So if in the other case, if the load is acting from this direction, how will the bending take place? Or how will the beam deflect? Something like this one. Okay. So previous case, the beam was deflecting in this shape. Now the beam is deflected in this shape. So now our axis or the neutral axis changes. So look at this shape. If I apply the load from this direction on this beam, the bending is taking place around this y-axis. Okay, so now my neutral axis is this one. In this example, if the load is acting from this one, from this direction, the bending is taking place around this z-axis, and my z-axis is the neutral axis. And in this one, my y-axis is the neutral axis. So can I conclude that the axis perpendicular to the direction of loading is the neutral axis, right?
Yes.
So the load is applied, for for example, in this one, the load is applied parallel to the z-axis, which results in the bending around y-axis. This is my y-axis. In this case, the neutral axis is the y-axis, which is perpendicular to the z-axis, which is basically my axis of the loading. So there can be infinite number of neutral axes in any type of structure. It completely depends on the type of loading. So for now, I can conclude that the axis perpendicular to the direction of loading is the neutral axis.
Sir, इस केस में तो y x axis और y axis दोनों perpendicular हैं.
Yes, exactly.
Like, to the direction of...
Yes, both, actually all three of these axes are perpendicular to each other. So now you have to look around this thing, that around which axis bending is taking place. So in this case, around which axis bending is taking place? No, I think it was you.
Yes, sir, y-axis.
You got it, right?
Okay.
So in this case, the bending is taking place around y-axis. So y-axis is my neutral axis. In this case, the bending is taking place around z-axis. So z-axis is my neutral axis. So this is the concept of neutral surface and neutral axis. Now, what are principal axes? Let me. If we have this cross section, and these are my centroidal axes, and at any point in a beam, there can be infinite number of axes. This one, or this one. So there can be infinite number of axes passing through a beam member. But what are the principal axes? Let me draw it again. Principal axes are the one around which the product movement of area is 0, is equal to 0, and the second moment of area, which is basically Ix, Iy, is maximum or minimum. Now, why is that important? What is product moment of area? Product moment of area basically represents the distribution of different types of area around this neutral axis. So if the product moment of area about any axis is 0, and around the same axis, the second moment of inertia or second moment of area are maximum or minimum, we will call them the principal axis. For example, in this case, if you see, there are numerous cases, and around each of the axes, for example, how we calculate Ix, that is BH cube over 12. So, for example, I say that this is my x-axis. So, around this axis also, I will have one moment of second moment of area, that is basically Ix is equal to BH cube over 12. But this second moment of area may not be maximum or minimum. So there will be only one axis or one set of axes around which this second moment of area will be maximum, and this product moment of area is 0. That one axis is known as principal axis. Let's look at this example now. In this case, this is my axis of symmetry as well. This is axis of symmetry. Also the principal axis and the centroidal axis. So one axis is performing the role of all three axes. What if I have a unsymmetrical section like a Z section? In this case, let's say this is my centroidal axis. In this case, I won't have any axis of symmetry. Now, can anyone tell that whether this Z section will have a principal axis or not? Anyone? Yeah. Are you listening?
Sir, yes, sir.
Yes. Will this unsymmetrical section have a principal axis or not?
Sir, I think no.
No. Anyone else?
Sir, I think होगा because
Where?
principal product movement of area 0 तो नहीं होगा ना?
What?
I think sir के product movement of area 0 नहीं होगा.
Actually, on this axis, if I will calculate the actually the let me tell you in simple word that if you have a symmetrical axis, then around this symmetrical axis, the product moment of area will be 0 because the distribution of area around this, for example, symmetrical axis is same. Okay, so the distribution of this area is same, and the product movement, and if I take the movement of all these areas separately, and product movement of area is basically summation of the movement of all the areas, then this summation will automatically turns out to be 0 in the case of symmetrical section. But in the case of unsymmetrical section, there will be some axis which can be an inclined axis around which this distribution or this product movement or the sum of the movement of area will turn out to be 0. Okay, so now remember this thing in mind that in case of unsymmetrical section, we don't have an axis of symmetry, but we will have a principal axis around which the sum of moment is 0, and this Ix or Iy or the second moment of area is maximum or minimum. So this is the concept of principal axis. So any confusion about this one? I think no. So this is the concept of principal axis, and the principal planes are simply the planes which are, for example, in this case, for example, in the case, in this case, let me go back. In this case, these are my principal axis, and these planes which are parallel to the principal axis are also called as my principal planes of bending. For example, these planes of symmetry in the case of this symmetrical section are the principal planes of bending as well. And this is what we discussed just now, that the plane of symmetry, if axis has a plane of symmetry, then it is automatically a principal plane, and it always coincides with the centroidal axis in the case of symmetrical section. But in the case of unsymmetrical section, it won't coincide with the centroidal axis, but as this statement suggests, that whether they have an axis of symmetry or not, they will have two perpendicular axes about which the product moment of area is 0, and that will be our principal axis. Now you have studied this Flexural formula as well, so we will just review it briefly. The Flexural formula is something like this one: sigma is equal to my over I. And this formula was calculated for the loadings which are acting or that contains an axis of symmetry of the cross section. For example, when the loads are acting parallel to this, let's me call this as a y-axis. So for this type of loading, you derive this formula, and we basically took two assumptions in this formula: that the plane cross section would remain plane and Hooke's law is applicable. So this is an important point to understand, that this formula was derived for the loads which are acting parallel to one of the plane of symmetry. So just remember this point, and we will discuss it in the next slide. So another assumption, or not the assumption, but actually another concept or type of loading that for which we derived this formula, this Flexural formula, was when bending was taking place about an axis which is perpendicular to the plane of symmetry or around the principal plane. So now this concept comes into play. For example, I said that the formula was derived for the loading which is acting parallel to the plane of symmetry. Now when the load is acting parallel to the plane of symmetry, where does the bending take place? Just like this example. Now the load is acting parallel to one of the plane of symmetry, and bending is taking place around one of the principal axes. Now, bending around principal axis, and for this case only, the Flexural formula is valid, that the bending must take place around principal axis. Now, let's suppose in this example, we have the loads in the plane of symmetry. And let's suppose if I apply the load on this from this direction. Previously, we have the loads in like straight direction or parallel to the plane of symmetry. But now if I apply the load in this direction, where will be my neutral axis? Perpendicular to this load, let me say this one. Okay, but this neutral or the bending is taking place around this neutral axis, but this bending is not around the principal plane, which is this one. So in this case, I cannot apply directly this formula. So I have to figure out some other methods how to apply this flexural formula when the load is being applied in this direction. We will discuss that later. So any confusion about this one? What? Okay. So now what is the symmetrical bending? Symmetrical bending again is the same thing that when the loading is parallel or perpendicular to one of the principal axis, or for that sake symmetrical axis in case of symmetrical section, then the bending will only be in the direction perpendicular to the loading, just like we discussed in the first slide. And then such bending is called as the symmetrical bending. For example, let's consider the example of this I section, and when the load is being applied in this direction, the bending is taking place around this x-axis, let's call it, and this type of bending is called as symmetrical bending. But the important point is that the loading should be acting parallel to or perpendicular to the principal axis. So I have another question. Can an unsymmetrical section have symmetrical bending? Anyone? Daniel.
सर अगर हम उसका प्लेन फाइंड कर लें तब तो मतलब सिमेट्रिकल प्लेन अगर कोई हो तो उसके अराउंड तो हो सकती है. अनसिमेट्रिकल बेंडिंग फिर उसी सूरत में होगी ना.
Symmetrical plane in the case of unsymmetric section.
Yes sir.
Will there be? What did we discuss in the first slide?
सर वो सिमेट्रिकल प्लेन तो कोई भी नहीं होगा, मतलब फिर उसमें एक डायगोनल वाला मेथड जैसे आपने बताया वो यूज कर सकते हैं.
There will be a that's not a diagonal method, that is basically a principal axis that which there won't be any principal or symmetrical plane, but there will be a principal axis. So if I apply the load parallel to that principal axis, then I can have a symmetrical bending in the case of unsymmetrical section as well. But let's just stick to the symmetric section for now.
मतलब सर हमने हर केस में हर चीज में ना हमेशा प्रिंसिपल एक्सिस को ढूंढना है और उसके अराउंड बेंडिंग कर देनी है.
Yes, if we apply the load around that axis, then we will get the symmetrical bending. But we are not going to do that. We are going to do the unsymmetrical bending because we can already solve the symmetrical bending scenarios. So for the symmetrical bending or the simple bending is the one which takes place about the principal axis. Actually, all these statements are the different ways of saying a same thing. So I have put that all in this slide. So you try to read it and try to understand or solve the puzzle basically. These are the same things but are said in a different fashion, just to avoid any confusion if you are reading different type of textbook or if you come across different type of problem. For example, for a symmetrical section to have a symmetrical bending, the plane of loading must be parallel to or contain a central axis which is also a centroidal axis. For example, this case, this is also the principal axis, centroidal axis, symmetrical axis. So when the loading is parallel to or perpendicular to these axes, then the bending that will take place is the symmetrical bending. Now, unsymmetrical section, just like I told you, can also have symmetrical bending, if the plane of loading contains the principal axis. For example, this Z section, this is an unsymmetrical section. And but if I apply the load parallel to, this is my one of the principal axis, if the plane of loading, this is the plane of loading and it contains the principal axis. So if I apply the load parallel to this principal axis, then the bending will take place on an axis perpendicular to this one, just like this movement. And then this bending is also called as symmetrical bending in an unsymmetrical section. Now, this is the important question. When does the unsymmetrical bending take place? If I have this beam that is going inside the paper, and in the previous cases, the load was being applied in this direction, parallel to this y-axis, which is basically the principal axis. So due to this type of loading, symmetrical bending take place. But what if my load is being acting something like this? And actually, before moving on to this topic, I want to show you one diagram. If I show you on this, if I show this loading on the straight section or the longitudinal section, how will I show this one? Let's suppose I will again show you like this load. So from this shape or from the longitudinal section, you just simply cannot assume that it is acting in this direction. For example, if the load is acting in this direction, how will I show it on the longitudinal section? Just like this one. Okay. Now, if the load is acting in this direction, again, in every textbook, you will see that they will represent it like this beam. So previously, we had this assumption, or we were solving only the symmetrical bending, so we didn't bother looking at the cross section. Okay, but now since we know the concept of unsymmetrical bending, so if I give you this simple beam with this load acting, you don't have to assume it that it is acting parallel to the principal axis straight away. You should ask for the cross section and say, what is the direction of this loading in the cross section? Because I can't show it because this is acting out of the paper. So I can't show it out of the paper. So in each of the textbook, you will find the similar kind of representation on the longitudinal axis. But you have to look into the cross section to know the actual direction of the loading. So any confusion about this one? Or you understand this concept, right? I guess you did. So what is, now let's move on unsymmetrical bending. Unsymmetrical bending is the one in which the loading is not acting parallel to or along the principal axis. So, for example, in this cross section, you can see that the load is acting at an inclination to this principal axis. Okay, so due to this load, the bending is take place around this axis. Now, this axis is the axis which is perpendicular to the applied loading, or this is my neutral axis. All right, so the bending is taking place around this axis. Now, if I ask you to calculate the stresses in this case, can you use this formula? Anyone?
Yes, sir.
I think only you are listening. Laiba, are you there? Hassan.
Yes, sir, we can use this formula.
Can you apply this formula? So you are saying yes. Naveed. Sarah.
We cannot.
Huh?
Sir, we cannot.
We cannot apply. Yes, we cannot apply this formula. Just like I told you in the previous slides, that this formula is only valid when the bending is taking place around the principal plane. So now, while for calculation of stresses in case of unsymmetrical bending, we have to resolve this inclined moment, or the moment that is acting on an inclined neutral axis, into two components.
Excuse me, sir.
Along,
Excuse me, sir.
yes.
Sir, मैं इसलिए कह रहा था कि ये एक्ट करेगा क्योंकि सर मुझे ये अगर ये लोड एक्ट कर रहा है तो उस डायरेक्शन में प्रिंसिपल एक्सिस क्यों नहीं हो सकता? मतलब ये देखें, ये बिल्कुल अगर कॉर्नर टू कॉर्नर डायगोनल ड्रॉ करें तो ये डिवाइड तो हो रहा है सर.
But it is, yeah, it is dividing like this one you are saying.
Yes sir.
It is dividing, but like I said, there can be numerous planes passing through the section, but you have to calculate two things. The product moment of area, that should be 0, and the second moment of area, that should be maximum and minimum. So around this axis, it is quite possible that these two conditions won't be satisfied. There will be only two planes around which these conditions will satisfy, and those are basically our principal planes. So now to solve this, we have to resolve this movement into two components, and those two components will be around z-axis or this y-axis, or I can say around this principal axis. So now if you have the moments around this, then I can apply this equation or the flexural formula, and I can calculate the stresses or the stress due to loading which is not acting on the principal plane, or the unsymmetrical bending stresses. So I will use this formulation to calculate. I will see where the load is acting. Then I will look into the direction of movement, that where the movement or around which axis the movement is being acting. Then I will resolve this movement into two axes, which are basically my principal axis, and then I will apply this flexural formula separately on both of those axes. And when I will take simple summation of this principal or the principal bending stresses, that will be my stresses due to the unsymmetrical bending. Now moving on to, I will explain these figures later. This is just to show you for now. Or let me just briefly explain it. What does these figures mean? Now, as you know that when we were solving the questions for unsymmetrical bending, we used to get this type of representation around the section. What does this mean? That this movement is acting in the counterclockwise direction or going inwards the beam. So at the top of the section, the stresses are going inside the beam. So they are basically causing the compression at the top. Okay. At the bottom, they are basically coming out of the section. So the tension is at bottom. Okay. So this is due to the bending which is taking place around the z-axis. And when the bending is taking place around the y-axis, what is happening on the left side? The stresses are coming out of the section. So that means for the same section, we have tension on the right side and the compression on the left side. Okay, so I will explain it later when we will be doing the sign convention. It is basically important for the sign convention. And for in the case of unsymmetrical bending, we will have the representation of stress something like this, which is basically the summation of the stresses around this axis. For example, if I want to compute the bending stress in this quadrant, what will I do? I will look into these two sections separately. Then I will say that for this case, I have the compressive stresses at this quadrant. And in this case also, I have the compressive stresses. So I will simply add them. In this quadrant, if I'm calculating the stresses, I have the compressive stresses for this MZ case and the tensile stresses. So I have to take the numerical difference of these two terms. Then I will get the bending stress in this quadrant if I want to calculate. And this is how you represent it for the unsymmetrical bending. We will come on to this again later. So now look at this example. This is a Z section. And in this Z section, the load is being applied parallel to the centroidal axis. Okay. So due to this load, the bending that will take place will not be a symmetrical, or I can say it will be an unsymmetrical bending. Okay. And now for this z-axis, as I have told you that there will be a principal plane or the principal axis which are at some inclination to this centroidal axis. And usually, if I want to induce the symmetrical bending in case of this Z section, what will I do? I will incline this Z section. Okay, so if I put this Z section at an inclination similar to this angle alpha, then the load will be acting parallel to this principal axis, and this is what you see in most of the roof system. When you have an unsymmetrical section, they will put it at an inclined shape so that they can get the symmetrical bending for this kind of unsymmetrical section. So you change the orientation, so you will get the principal axis in the straight quadrant. So let's say in the at 90 degree to each other and at 90 degree to the original centroidal axis. So this is one method to change the orientation, because it is sometimes not feasible to apply the loading in this direction. Loads are usually acting in the original horizontal and vertical direction. So if you want to induce a symmetrical bending in case of an unsymmetrical section, you will simply rotate it and apply the load in the vertical direction, and then you can get the symmetrical bending in there. So this first thing that we will be covering is unsymmetrical bending in case of symmetrical section. So as I have explained you already that in symmetrical section, unsymmetrical bending occurs when the load is acting at an inclination to the axis of symmetry, just like I have shown you in the example of the rectangle. And the neutral axis does not coincide with the axis of loading. You also know that the neutral axis is perpendicular to the axis of loading. But in the case of symmetrical or unsymmetrical loading, the neutral axis is not the one which is perpendicular to the, which is coinciding with the axis of loading. But why is that? Can anyone explain me this point? Anyone? Sarah, are you there? Unib, I think he is not in the class, right? Daniel.
सर मैं तो इधर ही हूँ, लेकिन I can't explain this.
अब्दुल्ला
सर वो सारे इतनी हैं, लेकिन अगर कोई माइक वगैरह खोलता है ना अक्सर, तो पे कनेक्शन ड्रॉप हो जाता है, नेट वीक होगा.
I think net is not that bad which you are making it. Abdullah.
Sir, I am okay with the internet.
Yeah, you are okay, so you should not take responsibility for others. Naveed. So next time I should be marking the attendance based on your mics, if your mic is working or not. Who is 424?
Yes, sir.
4. Who are you?
Shazib.
Ah, Shazib. So Shazib, can you explain it?
No, sir.
What are you doing?
सुन लो सर, नोट कर लो सर.
Okay. Okay, it's fine. You can turn it off. So actually, as you can see, that in this case, when the load was acting at an axis or at an inclination to this symmetrical section, for example, at this angle theta, then the neutral axis does not coincide with the plane of loading. What does that mean? Actually, this load will produce the bending around this z-axis and the bending around this y-axis. So my neutral axis will be at some inclination due to both of these moments. Okay, so that inclination means, for example, let's say I will call it an alpha. So that inclination won't be directly perpendicular to this applied load, because now I have to consider two types of movement, and because of these two types of movement, I have to calculate the resultant neutral axis, and that resultant neutral axis may or may not coincide with the plane of loading. So this is what this concept means. So how to calculate? Yeah. Okay. So the statement is that in case of unsymmetrical bending, the neutral axis of the cross section does not coincide with the axis of loading. So in the case when the load was acting like in one direction, it is basically producing the bending around this one axis only. So this axis is basically my neutral axis, and it coincides with the plane of loading, which is basically this one. Directly it is coinciding with this one. Or by coinciding, I would say that this neutral axis is at 90 degree to this plane of loading. But in the case of unsymmetrical bending, usually theoretically, if you would you can say that it is perpendicular to this plane of loading, but practically what happens that it is not exactly perpendicular or to this plane of loading. Why is that? Because first thing that comes is you apply the load, moments are produced, okay, not the neutral axis come into place. So when the moments are produced and we resolve these moments into two components, so the moments are being produced in two directions, this z direction and this y direction also. So the neutral axis is the one around which the bending stresses are zero. So there are many factors that come into place now. This moment, this y distance, this iz distance, this moment, this z distance, this iy distance. So we need to find out the plane where both of these stresses are zero. So when we are solving this and we will get a plane where both of the stresses are zero, may not be exactly at 90 degree to this plane of loading. It will be at some angle to this plane, and that plane, so the conclusion is that the neutral axis, just in the case of symmetrical bending, is directly, we know that the bending is taking place around one axis, it is perpendicular. But in this case, there are these three factors and two types of moments including. So theoretically, it can be at 90 degree, but practically it is not, because many factors come into place. Right? You got this concept?
Yes, sir. Thank you.
Yes, sir.
So how to calculate the stresses due to this unsymmetrical loading or unsymmetrical bending? First thing is we need to determine the inclination of the applied loading or the resultant movement. Just like I showed you in the slides, when the load was acting at some inclination to this cross section, we need to figure out what is this inclination. And the second thing is we need to figure out what is this inclination of this bending moment. Okay. And then we will resolve this applied load into two directions. And what are these two directions? Resolve this load along the direction of principal axis. One is this one, the other is this one. Okay. And another thing is we will represent the movement by the double-headed arrow. Okay. So what does this double-headed arrow means? Let me show you. Let's say we have this cross section or this rectangular cross section on which the load is acting at an inclination P. There will be a surface which is perpendicular. Let's say theoretically it is perpendicular, or I can call it as the neutral axis around which the bending is taking place. Now it is difficult to interpret how will this bending or is to show, it is difficult to resolve this clockwise or counterclockwise bending every time. So it can make things confusing. So there is another method to show this movement. We will show this movement by a double arrow. Okay. So let's say this load is acting in this direction or in this way, and due to this load, this clockwise movement will be represented by this double arrow to just to differentiate between the loading and movement. So wherever you will, in whichever section you will see the double arrow, you should understand that this double arrow movement is due to the loading that is being applied at a plane which is 90 degree to this plane of movement or to the neutral axis, right? So this is how we will represent the moments now. Now, the double arrow will be used to represent the bending moment as a vector, just to show its direction, that whether it is in clockwise or counterclockwise direction. I will explain you in the sign convention that how this convention works, how to show the double arrow in case of clockwise and in case of, yes.
सर न्यूट्रल एक्सिस और प्रिंसिपल एक्सिस को डिफरेंशिएट करने में इतनी कंफ्यूजन है. Isn't there any like an easy way to differentiate them?
Actually, the easy way is you will get used to it after solving the numerical problems. I know it will be difficult but in simple way, you can just say that the principal axis is the one around which the product moment of area is 0 and the second moment is maximum or minimum. But the neutral axis, you should always relate this neutral axis with the applied loading. Okay, so the principal axis has nothing to do with the applied loading, but the neutral axis has to do something with the applied loading. And what is it?
Can there be more than two, like more than one principal axis?
No, principal axis will only be one.
Okay.
Okay, there will be one axis in any cross section around which the second moment of area is maximum or minimum and the product moment of area is 0. Okay, but there can be infinite number of neutral axis. Neutral axis depends on loading and principal axis depend on inertia. So this is the easy way to remember. So then you will calculate the moments and resolve it into two components around this principal axis and simply apply the Flexural formula to determine the normal stresses caused by each moment component. And then we have to use the principle of superposition to determine the resultant normal stresses at any point on the section. So actually I will stop here. I don't want to go into the sign convention thing because it will make things complex. So I expect you to revise all these concepts. Actually, these things are very confusing and will confuse you in the problem. So try to read these slides in detail and understand each single line because everything that is mentioned in the slides is repetition of each other. So try to read everything clearly and understand each and every concept. What are the principal axes, axis of symmetry, symmetrical bending, unsymmetrical bending. And in the next lecture, we will move on to solve some of the numerical problems. Now, if you have any question, you can ask me. Anyone?
No questions, sir.
And I am giving you some kind of
these?
Yeah.
Will you share these? Will you share these lecture slides? Yeah.
Yeah, I will send you in CMS, and also for the structure analysis course, I have uploaded the slides. You can download them. Okay. So, and for now, I am giving you some leniency. I am observing that many of the students are online, but they are not listening to the lecture or maybe busy in some other work. So from next on, or when we'll be solving the problems, I don't expect you to act like this. It's not for my advantage. It is for it is the mutual benefit. I am giving my 100%, and I expect you to do the same. You will learn it. It's not the difficult thing to do. So if you have any question, you can ask me, or this is it from the lecture. Anyone? Okay, then this concludes our session, and we'll meet again in next week. I will inform you the timing, and thank you very much for your time.